Okay, welcome back Science 10s to our next lesson in Earth Science. This is looking at specific heat capacity. Okay, so to start this video, let's consider that you're at a lake in the springtime and the weather has warmed up. It's feeling nice and warm outside. There's no more snow on the ground. All the trees, the grass, everything's feeling very warm and the air is feeling really warm. Maybe they report the temperature to be something like 25 degrees. It feels very comfortable out. And then you see a lake, you're like, oh, it looks like a nice refreshing lake. I'm just going to jump in for a swim. And when you jump in or fall in this case, it feels much, much colder. Why is the water so much colder than the air around? Why is it so cold in there, but outside of the water, everything seems to have warmed up? It seems like the water is still cold from winter, and it still is. It takes a long time for that water to heat up. And how can that be if they've both been heated by the sun? How can they be different temperatures? This is our introduction into specific heat capacity. It means how much energy does it take to warm up different substances. And it turns out water has a very high specific heat capacity, which means it takes a lot of energy to heat up. So let's take a look in this lesson about calculating specific heat capacity. All right, so taking a look at the notes here, a specific heat capacity, how much energy it takes to heat up a substance. Okay, the unit's a little complex. We'll look at an example to explain that further, but it's joules per gram degree Celsius. Let's take a look at some numbers. Steel or metal has a pretty low number, 0.47, and water has a much bigger number, almost 10 times as much as the metal, 4.19. So looking at the definition, what does that mean? It means that steel takes a low amount of energy to heat up, and water takes a much higher amount of energy to heat up. And again, water is one of the highest ones. So if we apply heat maybe from the sun to the ground and the trees in the air, they don't need a lot of energy to warm up to temperature, but the water has got a big number, meaning it needs a big amount of energy to warm up. Okay, let's look at that unit a bit more in an example here. So the steel is 0.47 joules per gram degree Celsius, water 4.19. So let's talk about heating some steel and some water here. And I chose 1 gram because this kind of shows what the unit is saying. It's saying how much energy in joules does it take to heat 1 gram by 1 degree Celsius. Okay, so it's saying to heat both of these from 20 to 21, raise them 1 degree Celsius, and we're heating up 1 gram. It's going to take 0.47 joules to heat the steel and 4.19 joules to heat the water. So just imagine that to get them both to 21, it's going to take 0.47 joules for the steel, 4.19 for the water. Again, much more energy for the water. Okay, that's kind of what the unit means. But let's try to look at a different question where maybe instead of saying how much energy, we're going to apply a certain amount of heat to it to see how much it heats up. Okay, kind of like the sun beating down on everything in my previous example. So let's say we add 10 joules. It's a low amount, but let's say we just add 10 joules of heat to both of these from the heat of the element, and we're heating them up in the fry pan. Okay, just keeping with some easy numbers. How much is the temperature of these going to change? Well, now we have to think it takes a lot of energy to heat the water, not as much energy to heat the steel. Which one do you think is going to get hotter? I'll let you think of your answer for a minute, and let's find out what they're going to be. The water is going to warm up to 22.4 degrees Celsius, and the steel, 41.3 degrees Celsius. So because it doesn't take as much heat or as much energy to warm up the steel, when we gave them the same amounts, the steel heated up a lot more. How do we get to those numbers and how can you calculate them is what we'll show on the next slide. This is the equation for specific heat capacity. It looks a little bit intimidating, but it's Q is equal to mc delta T. Okay, let's break down what each part of this means. Q is our energy in joules. We're kind of used to that from some previous lessons. M, you may have guessed, is going to be mass, and for this course, we're going to measure it in grams. And C is that specific heat capacity that we were talking about. Okay, measured in joules per gram degree Celsius. The next part looks the most intimidating, but it's actually not too bad. There's a triangle, which is delta or means change. So change in T, you may have guessed T is temperature. So even though it looks like two things, it's actually just one number. Delta T is our change in temperature. So if it heats from 20 to 25, that number would just be 5. It's just looking at the change. So let's put that into example. Let's see how we could apply this to a question a bit different than my previous one with the frying pans. This one says if there's 750 joules are applied to heat just 50 grams of water that is starting at 15 degrees, what will its final temperature be? Okay, let's start with that equation. Q is equal to mc delta T. This one, what are we looking for? It says, what's the final temperature? I want to figure out the change so I can get that answer. How much does the temperature change is what I'm looking for. So I have to rearrange for T, or delta T, so we'll divide the M and the C to the other side. Divide by M and C, let's plug the numbers in here. So 750 divided by 50 and 4.19. Now I'm going to highlight here, we need to make sure we put double brackets. So we're dividing by this entire number. I know the units make it look a little messy, but 50 times 4.19, that's the number we need to divide by. So make sure you put double brackets around that. So we divide by that entire thing in your calculator. What we get for a change in temperature is just 3.5799, lots of decimals, but just around 3.5 degrees. Even though we applied 750 joules, remember water takes a lot to heat up, so you only get about 3.5 degree change. Now I want to emphasize that that is the change, because you might see a multiple choice question that says, is the answer 3.57 or 3.6? And that's not our final answer, because it says, what's the final temperature? Well, if it changed by 3.6, we're going to have to add that to our original 15. So we'd add that to become 18.579, and it would round to 19 degrees for our final temperature. Okay, those are kind of the harder ones with some rearrangements. Let's look at actually a bit of an easier one if you just have to plug in to solve, because this shows us that I put in 750 joules, it doesn't heat up very much. How much would we have to put in to maybe boil like just a cup of water is our next question. So how much energy would it take to heat 200 grams, a little bit less than a cup, but just 200 grams of water from 20 degrees around room temperature all the way up to 100. So this one we're just going to plug in. We're asking for how much energy we're going to solve for Q. I'm going to plug in 200 grams, 4.19 for the C, and this is where a common mistake students will put in 100 for the change in temperature, but we're looking at just the change. So from 20 to 100, the change is 80 degrees Celsius. Multiply all that in and look at this huge number. We get 67,040 joules, lots of energy to heat this water up to boiling. Now there's a lot of digits there. Since we're into the thousands, we're going to represent this as thousands of joules, which is kilojoules. So let's just put our final answer as 67,000 joules, or 67 kilojoules would be our final answer. So I hope that's helped you to understand and help you with calculations for specific heat capacity. Thank you so much for watching, and I'll see you in the next video.